This is a demonstration of how to solve the van der Waals equation for real gases iteratively to find out the moles of gas under non-ideal or real conditions. For this particular problem, a chemist wishes to study acetic acid, that's the gas that I've been given, at high pressures and low temperatures. Why are these conditions where a gas would act non-ideally? Well, see the lecture outline videos, and I will explore why that is. Now, what is your gas's boiling point? Google it. Well, I put my degrees Celsius one here. It's 117.9. That equals 391.1 Kelvin. You can use the 0.15 on your 273.15 or not. Either way works. C, use the ideal gas law to calculate the number of moles of your gas required to produce a pressure of 200 atmospheres in a 2.000 liter container at 200 degrees Celsius above your gas's boiling point. Believe it or not, 200 degrees Celsius over your gas's boiling point, we still will see some non-ideal character. So let's see. So PV equals nRT. Pressure is 200 atmospheres, 200.0 atmospheres. Liters is 2.000 liters. N is what I don't know. R is 0.08206. And 200 degrees Celsius above my gas's boiling point is 591.1 Kelvin. And now I can solve for N by plugging in my numbers. I've got 200 times 2. Let's see, you got it? Let's see if I can put it on. Okay, good. Divided by R, 0.08206. We're using the ideal gas law, so it's still the 0.08206. Divided by 591.1. And I get 8.246, and I am going moles of acetic acid that I would get, or moles of anything. This is the ideal gas law, and so it applies to all gases. Whether or not it's right or not, that's another question, but this is our ideal gas law estimate. D says, repeat the calculation part C, but use the van der Waals equation to obtain a more accurate value. The problem must be solved iteratively. To solve this equation iteratively, ask your instructor how, or see the instructions below. Well, your instructor is going to do it for you as a demonstration. Your answer for the number of moles must be correct to 4 significant figures. That's why I've given you everything with 4 significant figures, and I've solved for N with 4 significant figures. Well, the way in which you solve this iteratively is you take the ideal or the van der Waals equation, and I happen to have it right on the next page. Ah, there it is. One of these pages. There we go. P plus A, P plus A, N over V squared times V over N minus B times equals RT. And since I'm going to be interested in solving for the moles, I'm going to isolate moles by itself. So I'm going to divide through both sides by RT and multiply both sides by N. So now I have N by itself on the right hand side. I have N, let's see, so now I've got N cubed here, and I take this N away and I add an N there. So my new equation, P plus A N cubed over V. Does that work? Oh no, So I just have to put my n in somewhere. So I don't have to multiply it here and here. I'm going to put it in just this term. So I'm going to have p plus a over n over v squared. So that term is going to stay the same. Now I'm going to put it in this term, and I'm going to get my n to cancel out here. I'm left with v minus b times n equals n. So, and here's what I'm going to do to solve iteratively. I'm going to take all my values. I've got 200 atmospheres, 200.0 atmospheres. I've got on the separate sheet, I've got my A and B values. Here's my A and B values. For acetic acid, my A is 17.82 and my B is 0.1068. So A is 17.82, and I will give these to you. My B is 0.1068. My N is my, well, let's do V. V is going to be my volume. That's 2.000 liters. And that goes two places here. My B I have, my N, yes, let's talk about our N values. So our N value is going to be our guess. And we're going to put it both places, which means we have all of the numbers on the left-hand side. Then we're going to solve this side and get a number for n. And our initial guess is going to be based on our ideal gas law. So we'll put in 8.246. That gives us all the numbers on the left-hand side. Then we will solve for n. And instead of 8.246, we will get a number like 9.543, whatever it is. That is our new guess, which we then put back in, solve everything, get a new number. And iterative solving means you have an initial guess that you've gotten from some sort of estimate or similar equation. You put it in, and you basically keep plugging it in, getting it out, plugging it in, getting it out, plugging it in, getting it out, until this becomes a true statement. Until you get something like 10.64 moles equals 10.64 moles. When it's true to 4 significant figures, you know you're done. And it may take 5, and it may take 20 iterations. It's unclear how many it will take. It depends on your A and B values. And that's what we're going to do, is we're going to solve iteratively using this approach. Let me show you one iteration. So I've got 200, and I'm going to drop my units. 17.82, 8.246 divided by 2.000 squared times 2.000 minus B 0.1068 and 8.246 equals n. So I'm going to multiply this out, going up. This term here, 200 plus, well, let's do the squared part, 8.246 divided by 2 squared times 17.82 plus 200, 502.9 times 2 minus 0.1068 times 8.246 equals, I get 1.119 Well, let's give it a shot. So, oh, I'm sorry, I forgot my divided by RT. Divided by RT, R is 0.08206, and T is 200 degrees above my boiling point. My boiling point is 391, so now I'm at 591.1 Kelvin. So 502.9 times 1.119 divided by 0.08206 divided by 591.1. I get 11.60. So now this is not a true statement because I put 8.246 in as my moles on the left-hand side. I got 11.60 out. Now I'm going to go put 11.60 in. That'll be my second iteration. For my second iteration, I will now get, well, these numbers stay the same. Let's see, 11.6, I'll do in red. $11.60 divided by 2 squared times 17.82 plus 200 equals 799.5. 2 minus 0.1068 times 11.6 equals 0.761. Let me do that again. 2 minus 0.1068 times 11.6, 0.7611, so I'm keeping 4 sig figs. 0.7611 times 799.5 divided by 0.08206 divided by 591.1, 12.54. And then you keep going until the number you get out and the number you put in are the same.